Now we will continue calculating the mean energy of an ideal gas. If you remember, in the previous video we showed that there is an energy epsilon kinetic contribution which is given by three quantum numbers nx, ny, and z, and then there is the contribution for motion with respect to the center of mass, vibrations and rotations with one or more quantum numbers n sub I. Now, how do I calculate the mean energy? The mean energy per molecule is by definition a sum over all possible states, probability of a state R multiplied by its corresponding energy epsilon R. And remember, we're doing this for a non-degenerate gas. So if I substitute canonical distribution for the probability, I will get summation over all possible states e to the minus beta epsilon r Boltzmann factor epsilon r energy divided by sum over r e to the minus beta epsilon r, and this comes from normalization. And if I concentrate on this the term in the numerator, I see that the summation over all possible states e to the minus beta epsilon r can be written as minus the summation over all possible states derivative with respect to beta of e to the minus beta epsilon r. So the derivative with respect to beta would give me minus epsilon r, and because I have a minus sign, this becomes plus epsilon r. Because the derivative and the summation will commute, so it doesn't matter which one I do first, so I can write this as minus the derivative with respect to beta of the sum over all possible states e to the minus beta epsilon r. So I see that this summation over all possible states e to the minus beta epsilon r Boltzmann factor keeps appearing. I'm going to define z, capital Z, as the summation over all possible states e to the minus beta epsilon r. This basically is called the partition function. So that's called the partition function. This is for the molecule, for one molecule. Then I can write for epsilon bar the derivative with respect to beta with a minus sign of the partition function divided by the partition function. So you can see that this is minus 1 over z dz d beta, and basically that reminds me of the natural logarithm. I can write epsilon bar as minus the derivative of natural logarithm of the partition function with respect to beta. So that would give me 1 over z dz d beta. So the mean energy per molecule is given by minus the derivative of the partition function with respect to beta. Now let's consider the monatomic gas. So for the case of a monatomic gas, basically the task is to calculate the partition function. You can see that if I calculate the partition function by using this relationship minus del ln z del beta, I can calculate the mean energy per molecule. So this partition function z is the summation over all possible states. I have three quantum numbers n sub x equals 1 to infinity, n sub y equals 1 to infinity, and n sub z equals 1 to infinity, exponential minus beta pi square h bar square divided by 2m and x square over lx square and y square over ly square and z square over lz square, which are the kinetic energy terms given by the quantum numbers nx, ny, and z. So you can recall this result here. For the monatomic gas, we have found these energy levels. Now I can expand this exponential, so this exponential term, which is minus beta pi square h bar square divided by 2m n sub x square over l sub x square plus n sub y square over l sub y square plus n sub z square over l sub z square, because there are three terms in the summation here. This can be also written as the product of three exponentials, exponential minus beta pi square h bar square over 2m and x square lx square. This would be the first exponential. Then I would have exponential minus beta pi square h bar square divided by 2m and y square divided by ly square. And then the third term, exponential, so this is product, minus beta pi square h bar square divided by 2m and z square divided by lz square. So product of three exponentials. So you can recognize this as the partition function z can be written as also the product of three partition functions for each degree of freedom x, y, and z. So if I look at the definition of zx, zy, and zz, I would have zx partition function for x dimension and x equals 1 to infinity, exponential minus beta pi square h bar square divided by 2m and x square over lx square. This would be the x, and similarly I can write the y partition function, sum from ny equals 1 to infinity. I will have exponential minus beta pi square h bar square divided by 2m and y square over ly square. And similarly I can write finally the z partition function, sum from nz equals 1 to infinity, exponential minus beta pi square h bar square over 2m and z square over lz square. So then I have the total partition function is the product of zx, zy, and zz. So that will give me the final partition function. So now the question of how to calculate the partition function has boiled down to calculating it for one dimension and then basically multiplying for x, y, and z. Now you can see that if I go from nx equals n to nx equals n plus 1, if I go from one value to the next value, the successive terms in the sum will differ only slightly in magnitude. So I'm going to make an approximation, and I'm going to replace the summation with an integral, basically treating the quantum numbers as continuous variables rather than discrete variables in this approximation. So since I have successive terms in the sum, basically changing only slightly in magnitude, we can approximate the sum as an integral. And how do we do that? Well, let's just calculate zx. So this is going to be an integral. So I can take the midterms. So maybe I can say 1 over 2 to infinity, or I can neglect the difference between 1 over 2 or 0, because if you put 0 here, you're just going to get a term of 1. So I can start this, this is just an approximation, so let's start this integral from 0, exponential minus beta pi square h bar square over 2m nx square lx square d and x. And basically I'm going to make a transformation of variables. I will go to u square, so I'm going to define u square as beta pi square h bar square divided by 2m lx squared multiplied by nx squared. So this is going to give me for u beta divided by 2m square root 1 over 2 pi h bar over lx and x. So you can find from here that du is going to be equal to beta divided by 2m to the power 1 over 2 pi h bar over lx d and x. So that means I'm going to replace d and x with the following term: 2m divided by beta to the power 1 over 2 lx divided by pi h bar du. So I'm going to use these two transformations. So d and x will be replaced by this term, and u square will be replacing this term. And you can see that as nx goes from 0 to infinity, u also goes from 0 to infinity, so I don't need to change the limits in the integration. So zx will then become 2m over beta square root lx over pi h bar integral from 0 to infinity e to the minus u square du. Basically this is the integral of a Gaussian from 0 to infinity, and these types of integrals we have encountered before. If you go to the review of our mathematical notes, one of the results we had was this integral from 0 to infinity e to the minus alpha x squared dx is 1 over square root 2 pi over alpha, where alpha is equal to 1 here. So the answer for this integral is given here as 1 over 2 square root pi. So for alpha is equal to 1, the answer is square root pi over 2. So that's what I'm encountering here for this integral. So this integral is square root pi over 2. Therefore, we find that Zx must be 2m pi divided by beta to the power 1/2 Lx over 2 pi h bar. And I'm going to call this 2m pi to the power 1/2 together with 2 pi h bar, a constant b, so this is just a constant b, times Lx divided by beta to the power 1/2, where I have defined b, this constant, to be 2m pi to the power 1/2 divided by 2 pi h bar. Now you can see that this is going to be the case for the others as well. So basically I'm going to find out that z, the partition function, is b times Lx to the power Lx divided by beta to the power 1/2. That is the x partition function. Y is just going to give me Ly, b times Ly divided by beta to the power 1/2, and then I will have b times Lz divided by beta to the power 1/2. So the total partition function for this one molecule will be b cubed, the volume V, divided by beta to the power 3/2, where the volume V is the product Lx, Ly, Lz. So we can now take the natural logarithm of the partition function. It will be natural logarithm of V plus 3 natural logarithm of B minus 3 over 2 natural logarithm of beta. And if I calculate the derivative of natural logarithm of z with respect to beta, I will get minus 3 over 2 beta. Therefore, I will have for epsilon bar, mean energy per molecule, 3 over 2 beta. Because remember, epsilon bar was given by minus del ln z del beta. So there's a minus sign. So it's 3 over 2 beta. And beta is 1 over kT. So it is 3 over 2 kT. This is per molecule. That's the mean energy per molecule. And this result applies to monatomic gas. Now, if I extend this discussion to the case of polyatomic gas, so let me see. So I have done the monatomic gas case. Now there is the polyatomic gas. The energy values that I will use for state R will be given by mean energy of kinetic energy per molecule plus the term coming from rotations and vibrations defined with respect to center of mass. So since I have the first term equaling to 3 over 2 kT, I will have plus the mean value of, as a function of temperature, of the other types of motion, rotations and vibrations per molecule. So this is a simple extension. And the total mean energy, if I want to know the total mean energy of the full gas, the total mean energy will be capital E bar, that is sum over all energies of molecules mean value, and because the molecules do not interact, they have the same mean value of their energies, so this will be just number of molecules times mean energy of one molecule. So for n molecules, this is for n molecules. Now there is an important result here. I have found that the mean energy is only a function of temperature. It's independent of the dimensions of a container. This is for an ideal gas. So for an ideal gas, we find that the total mean energy is a function of temperature. It is independent of the dimensions of the container. Now, this basically comes from two results here. One, 3 over 2 kT, the mean energy per molecule for kinetic energy, translational kinetic energy. And for vibrations and rotations, because these are defined with respect to center of mass, whereas the kinetic energy was the center of mass translational kinetic energy, rotations and vibrations are with respect to the center of mass. They're independent of the dimensions of the container. Therefore, the total mean energy is independent of the dimensions of the container. But there's a word of caution here. If you have a non-ideal gas where you cannot neglect the interactions between molecules, for a non-ideal gas, if you change the dimensions of the container, because this is going to affect the mean separation between molecules, this would change the mean separation between molecules, and the interaction energy is a function of the distance between the molecules. The energy of the system, the total energy of the system, which has this potential energy term, will have a change due to the increasing or decreasing mean separation between the molecules. So for the ideal gas, we've only considered, if you remember, we have no interaction between molecules, free molecules. Potential energy term was 0. So we only consider monatomic gas, translational kinetic energy, polyatomic gas, plus the vibrations and rotations due to with respect to center of mass. We find that this potential energy term would come back if you have a non-ideal gas and the interaction potential energy is usually a function of the separation xyz between molecules, and by changing the dimensions of the container, since you would be changing the mean separation between the molecules, this would affect the potential energy term. Therefore, the total mean energy would depend on the dimensions of the container for a non-ideal gas. So let's review what we said. Well, we're using the canonical distribution to calculate the mean energy of one molecule in the ideal gas, and that is the Boltzmann term multiplied by the energy in state R divided by summed over all possible states divided by what we called the partition function. And we have shown that the mean energy is given by minus the derivative of natural logarithm of partition function with respect to beta. If we apply this for a monatomic gas, when you calculate the partition function, since you will know the mean energy by using this relationship between epsilon bar and z, I have basically expanded the partition function into three components, zx, zy, zz. So I see that the product of three exponentials give me the partition function z. And you can find that each successive term in the summation will only differ slightly, so you can replace these sums with an integral as a good approximation, where I have encountered a Gaussian integral from 0 to infinity, which gave me square root pi over 2. And finally, using also this transformation between nx and u, I was able to evaluate this integral to find that the total partition function was given by b cube b over beta to the power 3 over 2, where b was what I defined as a constant 2m pi to the power 1/2 divided by 2 pi h bar. So that is right here. And by taking the natural logarithm of the partition function and taking the derivative with respect to beta, I obtained minus 3 over 2 beta, which corresponds to a mean energy per molecule of 3 over 2 kT. For the polyatomic gas, in addition to this 3 over 2 kT, I would have terms coming from vibrations and rotations with respect to center of mass, but those would also not depend on dimensions of the container because they're with respect to the center of mass. And the total mean energy is just capital N times the mean energy per molecule. And for a non-ideal gas, on the other hand, I see that changing the dimensions of the container Lx, Ly, Lz would have an effect because it would change the potential energy by changing the mean separation between the